Here's a sentence that should not exist in modern commercial aviation. A major industrial nation with a space program, a nuclear arsenal, and decades of aerospace heritage had to learn how to build a jet engine from scratch. Not because they forgot how, not because the technology was too advanced, but because the world decided they no longer deserved access to it. This is the story of the PD-8, an engine that Russia was never supposed to need, and the jet it's being built to save. If you enjoy deep aviation documentaries that go beyond the headlines, subscribe, because this story doesn't end where most coverage stops. Let's go back. Not far, just to 2022. Before that year, Russia operated hundreds of Western-built commercial aircraft. Airbus, Boeing, CFM, Pratt & Whitney. Russian airlines flew them. Russian leasing companies financed them. Russian airports serviced them. And then, overnight, almost all of it became illegal. The sanctions that followed Russia's invasion of Ukraine didn't just freeze assets or restrict exports. They reached inside the cockpit. They targeted the aircraft themselves. Spare parts, software updates, maintenance contracts, engine overhauls. All of it cut off. For Western manufacturers, it was a clean break. For Russian aviation, it was an emergency that had no playbook. But here's what made the crisis particularly acute for one specific aircraft. The Sukhoi Superjet 100, Russia's flagship regional jet, was already flying, already in service, already carrying passengers, and it was powered by the SAM-146, a joint French-Russian engine developed by Safran and a Russian partner. When sanctions hit, the supply chain for that engine didn't just slow down, collapsed. And suddenly Russia had an aircraft it couldn't fly, and a gap in its domestic aviation network it couldn't fill. This is where the story actually begins. Russia is not a small country. That seems like an obvious thing to say. But in aviation terms, it has a very specific meaning. Russia spans 11 time zones. Hundreds of cities connected not by highways or high-speed rail, but by air. Remove domestic air service from Russia's regional network, and you remove the only connection many communities have to the rest of the country. This isn't a convenience problem. It's a structural one. The Superjet was supposed to be the answer to that problem. Developed in the 2000s, certified in 2011, the SSJ-100 was Russia's first new commercial jet since the Soviet era. It was designed specifically for short and medium-range domestic routes. City pairs that couldn't justify wide-body aircraft but needed something more reliable than aging Soviet turboprops. Russia invested heavily in it. Airlines bought it. Aeroflot flew it. The government promoted it. But the SSJ-100 was always a compromise. It was built using significant Western components, not just the engine. Avionics, flight control systems, landing gear, even some structural elements. Russia's aerospace industry had the ambition, but not always the supply chain independence. And that was a calculated bet that paid off during peacetime, and became a liability the moment geopolitics shifted. When sanctions hit, Russia had a choice. Ground the Superjet program entirely, or reinvent it. The answer the government chose was neither simple nor certain. They would build a new aircraft, the SJ-100, not SSJ-100, but SJ-100, a redesigned, re-engineered, domestically sourced variant. New avionics, new systems, Russian components throughout, and a new engine, not adapted, not modified, built from the ground up. That engine would be called the PD-8. Now, I want you to understand what this decision actually means, because it's easy to say, build a new engine. It is extraordinarily difficult to actually do it. Developing a civilian jet engine is not a matter of engineering talent alone. It requires decades of materials research, specialized manufacturing equipment, quality control infrastructure, a supply chain of hundreds of subcomponents, and thousands of hours of testing, real testing, under conditions that simulate everything nature and bad luck can throw at a turbofan. Russia had done this before. but largely for military applications. A military engine and a commercial engine are fundamentally different products. A fighter jet engine is built to perform. A commercial airliner engine is built to perform reliably for 20 years with minimal unscheduled maintenance across millions of flight cycles. The margin for error is completely different. And yet they began. PD-8 development started formally in 2019, before the sanctions, before the war, as if someone somewhere already knew the window might close. Here's something the headlines usually miss about the PD-8. It didn't come from nowhere. Russia had already been developing the PD-14, a larger turbofan engine for the MC-21 narrow-body jetliner. That program, built over more than a decade, represented a genuine investment in civil turbofan technology. The PD-8 inherited from that work. Same engineering philosophy, similar core architecture, scaled for a different aircraft class, the 8-ton thrust range needed for a regional jet like the SJ-100. But inheritance isn't the same as replication. Engineers couldn't simply shrink the PD-14 and declare success. Different thrust class, different operating profile, different performance requirements. The PD-8 program introduced 25 critical technologies. 17 of them had never been developed domestically before. Let that sit for a moment. 17 technologies that Russia, a country with nuclear submarines, hypersonic missiles, and a space station, had to develop for the first time for a civilian jet engine. That's not a criticism. That's a measure of how specialized and demanding civil turbofan engineering actually is. Military and civil aerospace exist in parallel universes of precision. And bridging that gap, under sanctions with a hard deadline and with an entire airline network waiting, is the story no one fully tells. Let's talk about what it actually takes to certify an engine, because this is where the PD-8 story gets genuinely extraordinary. The test campaign for the PD-8 was not a symbolic exercise. It was an exhaustive, methodical, brutal process. 1,449 flight hours accumulated on test aircraft. Additional bench test time. A flying laboratory, the Aviation IL-76LL, modified specifically to test the engine in real atmospheric conditions. And then there were the extreme environment tests. Icing trials in the Arkhangelsk region, one of the coldest and harshest operating environments on Earth. Not simulated. Real weather, real ice crystals, real atmospheric conditions that commercial engines encounter on northern routes. Bird strike tests, water ingestion, ice ingestion, fan blade failure simulations. Each test designed to answer a fundamental question. What happens when something goes wrong? Because in commercial aviation, the engine doesn't just need to perform perfectly. It needs to survive imperfection. But the test that stands out, the one worth describing in detail, happened in April of this year. A hail-ingestion test. For 30 seconds, engineers fired approximately 220 kilograms of ice projectiles into the running engine, at speeds of up to 240 meters per second. That's roughly 485 pounds of ice. In half a minute, at near ballistic velocity. And the engine kept running. That is not a small thing to say. A turbofan's fan section is rotating at thousands of RPM. The blades are precision-machined components operating under enormous centrifugal force. A severe hailstorm, the kind an aircraft might encounter on approach or departure, can deliver concentrated, repeated impacts to those blades in rapid succession. If the fan section fails under that load, the consequences can be catastrophic. The test is designed to replicate the worst-case scenario aviation planners have to account for. And the PD-8 passed it. Here's a detail that often gets lost in coverage of engine certification programs. The testing isn't just about whether the engine survives. It's about understanding exactly how it survived and what it looks like afterward. After every significant test sequence, the PD-8 was disassembled. Fan blades examined, bearings inspected, combustion chambers analyzed, every critical component compared against predicted performance models. This teardown process happened more than 100 times during the certification campaign. Why does that matter? Because certification isn't just about passing tests. It's about building confidence in a model. The data from those teardowns feeds back into engineering calculations, confirms that where patterns match predictions, validates that the design margins are real, not theoretical. It's the difference between an engine that passes a test and an engine that proves mathematically why it passed. And that distinction matters enormously for a program trying to earn the trust of regulators who have every incentive to be rigorous. Russia's Federal Air Transport Agency, Rosaviatsia, is now conducting exactly that kind of review. Certification materials submitted. Technical specialists engaged. The process moving forward. If the schedule holds, SJ-100 certification testing wraps in August 2026. That's not a guarantee. Certification timelines in aviation almost never are. But the momentum is real. ACT-7, the larger machine, 1530 now pull back. Because the PD-8 is not just an engine for a regional jet. It's a statement about what Russia believes it needs to build in order to survive as an aerospace nation. The B-200 amphibious aircraft, a platform currently powered by Ukrainian-built D-436TP engines, is also scheduled to receive the PD-8. Before the war, Ukraine and Russia shared aerospace supply chains stretching back to the Soviet era.
Motor sich in Zaporizhzhia.
Antonov in Kiev. Decades of integrated manufacturing. All of that is gone. Every engine that Russian aircraft relied on from Ukrainian suppliers now has to be replaced domestically, or the aircraft becomes unserviceable. The PD-8 is partly an answer to that problem too. And production has already been established. UEC Saturn's facility in Rybinsk, a city that has produced aircraft engines since the Second World War, is now building PD-8s for series delivery, not prototypes, series production. That is a significant milestone for a program that started in 2019 and has operated entirely under the pressure of sanctions, geopolitical isolation, and a domestic aviation system in crisis. Let's be honest about what we're watching. Russian aviation is not out of difficulty. The SJ-100 faces enormous challenges beyond the engine. Avionics, certification acceptance, airline fleet planning, pilot training for a significantly modified aircraft type, and the global aviation market, the one that operates on ESA-type certificates, on ICAO standards, on lessor confidence, that market remains effectively closed to Russian-developed aircraft. The SJ-100 with PD-8 engines will not fly into Frankfurt or Singapore. It will not appear in Western airline fleets. It will not compete against the Embraer E2 or the Airbus A220 on the open market. But that's not the point anymore. The point, the real strategic logic, is self-sufficiency within a closed system. Russia has approximately 170 million people. Hundreds of city pairs that require air service. A domestic airline sector that cannot function without regional aircraft. If the SJ-100 with PD-8 engines can be certified, produced, maintained, and operated entirely within Russian supply chains, then Russian regional aviation becomes independent of Western decisions. Not competitive globally, independent domestically. That is the calculation being made here. Not winning a market, surviving without one. Here is the thought I want to leave you with. We are living through an era of aerospace fragmentation. For 70 years, the global aviation industry was built on the assumption of interdependence. American engines, French avionics, Japanese composites, Brazilian subassemblies. It was messy, complex, globally distributed, and it worked. That system is fracturing. Russia is building its own engines. China is certifying its own jets. The supply chains that connected aerospace industries across geopolitical lines are being severed, not gradually but suddenly. The PD-8 is a product of that fracturing. It exists because the alternative was an aviation network that simply stopped working. And whether you read that as a story of resilience or a story of what happens when globalization breaks down, depends entirely on which side of that fracture you're standing on. The engine hasn't been certified yet. The aircraft hasn't entered service yet. The story isn't finished. But 1,449 flight hours. 220 kilograms of ice at 240 meters per second. 100 teardown inspections. Someone is building something, and they are building it because they have no other choice. If this documentary gave you something to think about, subscribe. Every episode goes deeper than the headline. Every story reveals something about where aviation is actually going. And in the comments section, I want to know what you think. Is this industrial self-sufficiency? Or is it the permanent fragmentation of global aerospace? The answer might matter more than the engine itself.